Welcome back, ladies and gentlemen. Today we're going to talk about section 3.3. And this is a big piece of what calculus is being able to take information from the derivative and apply it to what the function is doing. Today we're going to focus on something called the first derivative test. Yesterday we spent a lot of time on finding critical values. Today we're going to examine what the derivative is doing near those critical values and make some conclusions about the function. A lot of this should be pretty intuitive to you right away, because I think you can answer these two questions. If I tell you, for instance, that f prime, the derivative is greater than 0, that is, that f prime of x is positive, you can tell me something about that graph probably by now. And if you can't, this is the day to learn. So if I tell you that f prime is positive, that means that the original graph must have been increasing. And if that were true across the entire graph, I don't know how it is increasing, what the curvature is or how steeply it is, but just off of that, I can conclude that the f of x would be increasing based off of that one piece of information. And by the same reasoning, if I tell you that f prime of x is less than 0, or if f prime, the other way of thinking about it, that is f prime is negative, then we can say that f of x must have been decreasing on whatever interval we're talking about. Or if we're talking about the whole thing, then it's decreasing over the whole thing. And again, I don't know about how fast it's decreasing off of this one piece of information. I don't know what the curvature of the function is, but I know that in general, the graph of f should go downhill from left to right at all points based on that one little piece of information. Now, what we're going to talk about today is we noticed that yesterday when we sketched out the derivative near a maximum, we noticed that the derivative could either be undefined or it hit a value of 0 at those maximum values. And today we're just going to put all this information together. So if I have something increasing until it hits a critical value, and then afterwards it's decreasing after that critical value, well, then we probably achieved some maximum value. And of course, just the converse of that, if it was decreasing up until the critical value and then increasing afterwards, then we should have hit a minimum value. Before I move on here, I just want to throw out one random vocab word, monotonic, which means that a function that is always increasing or always decreasing, so it doesn't change direction vertically. So random vocab word, you may see it, you may not, but it's important to know that word should it come up. I've seen it on a few AP exams. So this is the heart of the lesson today, which is if I say that f prime of x is positive, say up until a value of 4, and I say that it's negative past the value of 4, what can you conclude? Well, you can conclude, again, you don't know about the curvature of the graph, but the function should be increasing up until a value of 4 and decreasing after a value of 4. The other thing I want you to notice in this statement is that we've used an open interval to describe the intervals of increasing and decreasing in this sentence. And that is something that we're going to remain consistent on. We're not really going to include the endpoints. In other words, we're not going to say that a function is increasing at its maximum value, like at that spot where the tangent line might be 0. We're just going to ignore the endpoints on all these intervals. Okay. The second piece, so now I say f prime of x is negative before 4, so it should be decreasing into the value of 4, and then after 4, it's positive, and that would mean that it would be increasing, suggesting that we probably hit some sort of minimum value. So if we have this piece of information where we're decreasing into it, we've got a tangent line of 0 at 4, we'd have to do a little more work to prove that, and then increasing afterwards, it's very obvious that we've hit a minimum value then. Okay. There is one other case, though, where the sign of the derivative doesn't change. So let's say it was negative to begin with before 4, and it's negative after 4 as well. So that would just mean that we're decreasing into some sort of critical value. It might be a derivative equals 0 or a derivative is undefined situation. So we might have that situation, but then afterwards it is also continuing to decrease. And in that case, we would not necessarily be able to say, well, we would say that there is not a minimum or a maximum value occurring. You take all of these three pieces of information and put them together, and you have something called the first derivative test. And I would encourage you to look at this up on Schoology. And it simply states what we just said. Part 1 says if f prime changes from negative to positive, then we're going to have a relative minimum wherever that occurred. Part 2 says if f prime changes from positive to negative, then we're going to have a maximum at that critical value. And the third part says that if the f prime, or if the derivative does not change signs on either side of the critical value of question, then we can't conclude, well, we can conclude that there is neither a minimum or a maximum value. So this is a theorem, and if we were asked to justify why we believe there's a minimum or a maximum, we are actually going to reference this theorem, and we're going to use language like this. We say, okay, I think there's a maximum at this point C that we're talking about because, and okay, this is the part where you have to explain to your AP reader that you know what you're talking about, because f prime changes sign from negative to positive at an x value of C. Okay, you need all those words stretched together. We're going to practice writing them down a few times just so that we know, so we can structure exactly how, just so we know exactly what to do when we are asked to justify our responses. Okay, so let's take a look at a function today, and you can pause the video right here and copy down this function, x to the 5th minus 20 thirds times x to the 3rd. And there are two tasks. I want you to find all x values at which any extrema occur, and then I also want you to describe any intervals of increasing or decreasing. And just like yesterday, we're going to go, basically the process is go find any critical values, so any point where the derivative is either 0 or undefined, and then we're going to examine, the extra thing that we're going to do today is we're going to examine what happens on either side of every critical value. And I'll show you a nice way to organize your information here. So if we're doing part A, okay, first we want to find any critical values. So any x values where any extrema may occur, and we're going to do some further analysis to decide that yes, they definitely do occur there. Okay, so first thing I need is a derivative. So if I take the derivative of f of x, I'll get f prime of x, and we'll just apply the power rule here. So 5x to the 4th. When I bring that 3 down on the second one, that 3 is going to cancel, so I have 20x squared when I do that. Now we want to find when this is equal to 0, so I'll set it equal to 0. This is a polynomial, so it's never undefined, so we don't have any critical values where the derivative is undefined, but we should be able to at least attempt to solve this problem. And we're going to try to go totally without a calculator today. I don't know how that's going to go, but again, the upcoming test is without a calculator, so we're just going to practice all our techniques without calculator. Okay, this looks pretty factorable, so let's pull out a 5x squared. That would leave us with an x squared minus 4, which is further factorable. So we'll go 5x squared times x plus 2 and x minus 2, suggesting that we have critical values of x equals 0 and positive and negative 2. Okay, so we got 3 critical values there. Okay, and our job is not today just identify those or just to test them. We don't, I mean, plugging those into something with the 20 thirds there, that does not look like a whole lot of fun. So instead what we're going to do is we're going to do an analysis of what the derivative is doing. So the way I do this, just to be clear, what I'm about to do is not sufficient explanation for an FRQ, but it's a way of organizing the information so that I can then write out a formal sentence about why I believe there's a maximum or a minimum at a certain place. Okay, so what I do is I draw a number line, and I put my critical values on it, -2, 0, and 2. And then on the top of the number line, I'm going to label it f prime of x, and on the bottom of the number line, I'm going to label it f of x. Okay, and what we're going to do is we want to know what f prime is doing on each of these intervals that are in between, not at, the critical values. Okay, so for instance, if I would like to know what the derivative is doing right here, I'm going to choose an x value of negative, something smaller than -2. Okay, so let's just try -3. And I don't necessarily need to get a number. I just want to know whether the function is positive or negative. So I like to look at this line right here. I'm not going to fully calculate what f prime of negative 3 is. I'm just going to figure out whether it's positive or negative. So I'm going to go f prime of negative 3. And the way I'm going to do that is, you see how I have three things multiplied together? We just use that fact to solve it. I'm just going to examine if I plug in a negative 3, which of those are positive, which of those terms are positive and which are negative. So if I plug in a negative 3 into this 5x squared, I will get a positive number. I don't care what that number is, but I know that it's going to be positive. So I know I have a positive thing. And then if I plug in a negative 3 into this x plus 2, I will get a negative thing. And then if I do that again on the x minus 2 term, I will also get a negative thing. So that means I have a positive times a double negative, which would overall be positive, meaning that my function is positive right there, or my derivative is positive, and my function should be increasing on that interval. And I continue this process with points in between the critical values that I care about. So the next one, a good logical choice would probably be negative 1. Usually 1, negative 1, and 0 are really easy values to calculate with. So if you have to perform a calculation. Sometimes you do, sometimes you don't. If I plug in a negative 1, well, see that 5x squared term is always going to be positive. So I don't even have to think about that one, which is kind of nice. If I plug in a negative 1 to the second term, that x plus 2, I will still get a positive number. Okay? Now it is now a positive number. It wasn't before. And now if I plug in a negative 1 here, I will get a negative number. So now I have something positive times something negative. So overall, the derivative is negative on that interval, which means that the function itself is decreasing. And right here, I've changed from increasing to decreasing on my original function. So I already know that there's a maximum value right there at x equals negative 2. And then we just continue this analysis. So let's go f prime of 1. Again, that first term is always going to be positive. If I plug in 1 there, that's going to be positive, and if I plug in 1 there, that's still going to be negative. Okay, so it's the same result as the previous one, so it's still negative, which means my function is still decreasing. So here, check this out, my function, my derivative stayed negative over a critical value. So that's probably a situation where I'm decreasing. If I just sketch this out, I know I probably have a horizontal tangent line or something like that. So I'm decreasing into this horizontal tangent line and then decreasing afterwards. Okay, and my negative 2 tangent line, we got a value of 0. All right, so I'm probably going up and then down, and then I got a little flat spot, but I'm continuing down, and then we'll see what happens here. So f prime, last one, got to choose something bigger than 2. Let's go 3. Again, that first term is always going to be positive because it's squared. That term is extra positive, and now that I have a number that's larger than 2, this is now going to be positive. So this is all positive. So now we can see a change in value here. So at 2, I had a derivative value of 0, so I've got a horizontal tangent line. And then afterwards, I'm going upwards. I'm increasing afterwards. So the function is increasing. So I've kind of got a pretty good sketch going right here of what I think my function looks like. Okay, and it was a polynomial to start with. It was an odd polynomial, so that's all matching up. So I can use all those just to kind of say, okay, so that means that I probably have a minimum value right here. Okay, in fact, I can say that for sure. Okay, I can say f of x, well, I'm not going to use capital F of x has a local or relative max at x equal negative 2 because f prime of x, I'm being very specific. I didn't say the function, I didn't say it. Okay, I'm being very specific. F prime of x changed signs from positive to negative. And that's basically exactly what the first derivative test says. And then we can say the similar thing. F of x has a minimum at x equals 2 because, and it just takes a little while to write out, f prime of x changed signs from negative to positive. And again, if I were doing a test, I'd probably spell out the word negative and positive just to be clear. Okay? So we've identified maxes and mins, and we've concluded that as we tend towards infinity, the derivative is still negative, and as we tend towards, if I tend towards negative infinity, the function is still decreasing or increasing on that interval, and it is still increasing as we approach infinity. So we don't have an endpoint of this interval in question. Okay. The second bit was describe all intervals of increasing or decreasing. So if this is where this map comes in, okay, so now I can see that f of x is increasing. I can say f of x is increasing anywhere the derivative is positive, and we found that to be from negative infinity to negative 2 and on 2 to positive infinity. Okay, and I could justify this, and I could say because f prime is positive on these intervals. Excuse the handwriting, it's been a long day. Okay, and then we can say f of x is decreasing anywhere that derivative is negative, so that would be between negative 2. Do we want to exclude 0? Probably. So I'm going to say 0, and then I'm going to pick up and 0 to positive 2 because f prime of x is negative on these intervals. And that's how the first derivative test works. So we can get additional information about what the function is doing, whether it's increasing or decreasing before and after a critical value. Okay, and if you wanted to see exactly what was happening, you can always plug it in on Desmos and see what's going on. You can see that we achieve a maximum at negative 2, a minimum at 2, and then we, of course, see that flat spot right in the middle horizontal tangent line at an x value of 0. Well, let's move on to the next problem. Take a moment, copy this one down. We're going to do all the same things. Basically, go find our max or mins, if there are any, and then describe any intervals of increasing or decreasing. Okay, this problem, you might be tempted to do product rule because there's two terms being multiplied. If I can avoid using product rule, I would love to. So I'm going to take the moment to first simplify g of x. I'm going to distribute that x to the 3/5, and I'm going to use the rules of exponents to do so. So I'm going to have 4 times x to the 3/5, which is going to get a little ugly, I admit. Okay, that's fine. But then when I distribute it onto the x, I'm going to take 1 plus 3/5. So I'm going to go minus x to the 8/5. So I'm adding 5/5 to 3/5 to get that. So I'm adding 1 to the exponent that was already there. And now I'm just in a little bit better form to take a derivative. So I'm going to go ahead and take a derivative this way. And I will get 12 over 5x to the negative 2/5. Oh, that's starting to look really ugly. And it is, I agree with you. But this is just the way it is sometimes. So we'll bring this down in front, so 8/5, and then we'll drop that by 5/5 or 1, and we'll get 3/5. Okay? And now let's just rewrite this. I have a negative exponent. So again, we're looking for critical values. That's where the derivative equals 0. So let's just take a look at that. So I got 12 over 5 times this would be a 5th root of x squared, if I just convert that exponent. And the reason I want to do that is now I see, okay, this is undefined at x equals 0. So that's going to become one of my critical values. So g prime of x is undefined at x equals 0. This one, let's just rewrite it, 8/5. Again, not so nice, but it's going to work. X to the 3rd inside there. Okay? Now, we go ahead and solve this for 0. So let's bring this 8/5 over. I'm going to combine the numerators here, so I'm going to write this as a fraction. So I'm going to go 8 times the 5th root of x to the 3rd over 5 equals 12 over 5 times the fifth root of x squared. And then I can probably do a little cross multiplication. So we got 60 equals 40 times, let's say we got x to the 3/5 times x to the 2/5. Well, that's awesome because that combines to be a power of 1. So I have 60 equals 40x. Didn't think that was going to get that simple, okay? But then we solve that and we get 3/2, or 1.5 is x. So there's another critical value. So we've got a critical value of 0 because the derivative was undefined, and we got a critical value of 3/2 because the derivative was 0 there. So I'm going to do another number line. I'm going to label it g prime of x. I keep trying to want to draw f. And then g of x. And then I'm going to put 0 and 1.5 on the number line. And I'm going to examine what happens when I plug in a number less than 0. So we'll do g prime of -1. Something in between 0 and 1.5. I suppose that 1 would work quite well for that. And something larger than 1.5. So g prime of, let's say, 2. And we'll figure out which each one of these are. Which version of g prime do I want to use? Probably this guy up here. We'll see. Okay. We'll see how this works. I can take a fifth root of 1 pretty easily. I can take a fifth root of -1 pretty easily. I can't take a fifth root of 2 very easily. So maybe I want to do something in this one that I can take the fifth root of a little bit easier. So let's do a 32 there. Because then I can take the fifth root of 32, and that's just a 2. So I'm kind of thinking ahead here. All right, g prime of -1, I would have 12 over, I might want to use this second step actually. I'm going to use this definition of it right here. So I'm going to go 12 over 5 in a different color. And I am going to take the fifth root of -1 squared, which means I got a +1, so that is 12/5 minus, and then if I do a -5 here, the cube root of -1 cubed, and then a fifth root is still -1, so that's actually plus. So basically I have 12/5 plus 8/5, which is, I don't care, it's positive. Okay, that's all we care about. G prime is positive on that interval. Okay, if I do the same thing with a +1, I'll still get this 12/5. Okay, but then I will subtract 8/5, and that is still positive. Okay, so we got a positive right there. And then this one, if I plug in a 32, remember if you have a fifth root of 32 to the third, that's what we're doing right here. We can switch the order of this. We can take the fifth root of 32 and then raise it to the third power. We can do that. Okay, so if we do that, if I take the fifth root of 32, that is a 2, and then if I square that, that is 4. Then I have 8 over 5 times, that would be 2 to the third times 8. Yeah, okay, so we got that. So it looks like that is 64/5, and that's a smaller number, so it's a larger negative number. So this is going to be negative overall. Again, I don't care what that number is, I just care that it is negative. This is pretty tedious math by hand. I wouldn't fault you for grabbing a calculator at this moment, but nonetheless, we have found that it is increasing. It is still increasing. So again, there's no maximum value at 0. We might have a flat spot or some other issue. And then right here, we have an increasing to decreasing situation. So this is going to be a max right here at 1.5. Okay, so we can conclude that, this is a g, sorry, I keep doing that. G of x has a max at x equal 1.5 because g prime changes from positive to negative at x equals 1.5. Okay, so we conclude that it has a maximum at that point. And then we can also say that it's increasing everywhere. Okay, so we can say g of x is increasing on negative infinity up to 0. I'm going to exclude 0, and from 0 to 1.5. And then I can also say g of x is decreasing on 1.5 onwards towards infinity. So there's our conclusions. There's our intervals of increasing and decreasing, and there's our max or minimum values. Now there's one question I didn't have in here. I don't know what this function looks like at all. This is it's a weird function, right? I'm curious what happened at that critical value of x equals 0, because we didn't get a maximum, we didn't get a minimum or anything like that. So let's take a look at the graph here and just make sure that we're on the right track here with all of our stuff. You'll notice that there is our horizontal tangent line right there. That's the maximum value that we found. It is decreasing after that, and it is increasing before that. And it looks like the critical value occurred from a vertical tangent line, and that's why we got that critical value popping out of the algebra. Okay, let's move on to our next problem. Let's go on to this one. Okay, this one's phrased a little bit different. This says, consider the function f of x of 1/2 x plus cosine on the closed interval from 0 to 2 pi. Take a moment, copy down that problem. This problem is phrased different. It just says find all extrema. So that means that it's looking for absolute mins and maxes, and it's looking for relative mins and maxes. Okay, so just as always, we're going to take a derivative. So f prime of x equals, I'm just going to write it as 1/2 minus sine of x. There's no chain rule or anything to worry about, so that's a pretty simple derivative. I kind of like it so far. All right, that derivative, this is a combination of a polynomial and a trig function, just sine of x. So there are no discontinuities or undefined areas. So we don't have to worry about those. Okay? Did I spell that right? Discontinuities. Yep, sure. Probably. Moving on. All right, set it equal to 0. 1/2 minus sine of x. All right, solve that thing. All right, where does sine of x equal 1/2? Think about your unit circle. That happens at x equals pi over 6 and 5 pi over 6. Okay, so if we examine like a number line chart, and we label f prime of x up top and f of x on the bottom, and I set up my little table or my line, I'm going to put pi over 6 here and 5 pi over 6 here, and I have to check the values in between there. Okay, these critical values may result in a min or a max, but I also have to check the endpoints too. So we could do all that. So before I go check the endpoints, I just want to check the increasing and decreasing nature of this function to make sure I don't get like an increasing and then increasing after the point as well. So let's talk about f prime of something less than pi over 6. So that, I suppose, 0 would work nicely. That would be 1/2 minus sine of 0 would be 0. So that would be positive right there. Okay. Choose something on this interval, something between pi over 6 and pi over 6. That would be, let's choose pi over 2, I suppose. So f prime of pi over 2 is 1/2. Sine of pi over 2 would be 1, so that is negative. Okay, so we're alternating positive and negative here. I imagine we'll do the same thing here. And then something beyond 5 pi, so probably, let's just do pi right there. 1/2 minus sine of pi is 0, so that's positive. Okay, so it looks like we have a max at pi over 6, and we have a minimum at 5 pi over 6. Okay, we also have to check the endpoints. Okay, so the endpoints were 0 and 2 pi. So I'm just now I'm gonna go to the actual function itself and figure out exactly how high each one of these things is. Okay, because we want to find the absolute max in this situation. Pi over 6, 5 pi over 6, and 2 pi. So I'm putting in the endpoints as well. Endpoints to check to see how high they are. Okay? And if we go into the original function, 1/2 cosine. So 1/2 times 0 plus cosine of 0. That would be 1. Okay? 1/2 times pi over 6 plus cosine of pi over 6 would be square root of 3 over 2. Let's grab a calculator for that one. That is 1.128, so I can put that 1.128. At this point, I could probably just grab a calculator and do a table. There's no shame in that. In fact, let's do that. So if I type all this into my calculator, at 5 pi over 6, the function is 0.443, to 3 digits anyways, and then at 2 pi, it is 4.142. So we got an absolute max right there, and we got an absolute minimum right there. And then this must be a relative min. Yep, and then this is a relative max. And we can go confirm that by graphing it if you wish. If you're curious, this is what the function looks like on that interval. And you can see we got a relative max there. Well, that's our relative max. We got our absolute min, and then we have our absolute max up there. Cool. Everything that we did checks out. So we said minimum at 5 pi over 6 and maximum at pi over 6, right? That's true. So check out that chart right there. We said that. We could have stated it more formally, but I'd say we're good to go. We're going to move on. Last problem right here. Copy it down. This time is another one where we have to examine just the interval. And again, we're trying to find all extrema, absolute, and otherwise. So take a derivative. Okay, this is just a polynomial, so we shouldn't have too much problem, I don't think. So let's see, we got 12x to the third minus 48x squared plus 36x. Everything's got a 12x in it. We can set it equal to 0 and factor. Okay, so everything's got a 12x in it. X squared minus 4x plus 3. I can factor that some more. 12x minus 3, x minus 1. And from there, we get critical values of x equals 0, x equals 3, and x equals 1. So those are all my critical values. And I can put all those on a number line. Go 0, 1, 3, 0, 1, 3. Label it up. H prime of x up on top, h of x on the bottom. Then I got to do that trick where I'm multiplying 3 things together and I don't care what the answer is, but I care about whether it's positive or not. So something less than 0. Let's go with a -1. Those are always easy. Something between 0 and 1. H prime, let's go of a half. And something between 1 and 3. So let's go h prime of 2. And something larger than 3. So h prime of 4. Don't have anything weird roots this time. So let's see how we're doing. Okay, if I plug in a -1, I'm going to have a negative thing times a negative thing times a negative thing, which will be a negative thing. So my derivative overall is negative in that region. If I plug in 1/2, I will have a positive thing times a negative thing times a negative thing. So that will overall be positive. If I plug in a 2, then I will get a positive thing, I will get a negative thing, and I will get a positive thing, so that would be overall negative. Looks like we're just going to alternate this time. Maybe, we'll see. Last one. If I plug in a 4, I'm going to get a positive thing times a positive thing times a positive thing, so that would be positive. So we have decreasing on up until 0, increasing between 0 and 1, decreasing between 1 and 3, and increasing thereafter. Okay, so it looks like we have a min, we have a max, and we have another min right there. Okay, so we do want to check this along with, if we're asked for absolute extrema, then we want to check this against the endpoints as well. So I will include those x values of -1, right? -1 and 4. So -1, 0, 1, 3, 4. Figure out what h of x is there. So if you want to figure out what h of x is there, there's no harm in grabbing a calculator and figuring it out on the table. We just wanted to do the analysis by hand, basically. So 37, 0, 5, -27, and 32. So there is an absolute min. And we identified it as a minimum, so that's always a good sign. And then there is an absolute max. That value was not on our sign chart, our little sign number line there, and that's because -1 was not a critical value, it was just an endpoint. Otherwise, we've identified this as a relative min then, because it's not the absolute. Then this would be a relative max, and this would be another relative max, because it is increasing up until a value of 4. We can see that right there on our little sign chart. Okay, and if we just want to inspect to make sure that we did it all right, that's what it looked like. So there's our absolute max. That's what we said. We got a relative min, a relative max, a relative or an absolute min down here, and then we have another relative max right there. That's all I have for you today. I'll see you next time.